All right, welcome in. We are once again in chapter 3, thinking about kinetics. In this video, we will be looking at the Arrhenius equation, a mathematical approach to collision theory. As we recall, collision theory says that in order for our reaction to occur, we need to have our molecules collide. On top of that, we need to have sufficient energy when those collisions happen, and oftentimes we need a very particular orientation when those collisions happen. This theory allows us, some intuition about how and why our reactions occur, and it tells us that changing the temperature of our reaction should change the rate based on two different mechanisms. When our temperature is higher, our molecules have more energy and bounce around faster. Well, based on that, we'll have more collisions. And separately, when those collisions occur, there will be more energy in each average collision. Excellent. Our collision theory should be able to explain our rate laws. As we saw in the last video, our rate law says that, how fast our reaction goes, that rate is equal to some rate constant times the concentration raised to some exponent. Our plan now is to give some mathematical approach to our collision theory that ties in to our rate law expression. The way that we'll do that is known as the Arrhenius equation. The Arrhenius equation describes our rate constant in terms of, our reaction coordinates and the activation energy, as well as temperature effects and, some way to account for the necessary orientations. Here is the Arrhenius equation. It says, K is our rate constant. This is equal to some constant, some value A, known as the frequency factor, a way to account for the orientations of our molecules. This frequency factor is multiplied by an exponential factor, E raised to the negative activation energy divided by R, the gas constant, times T, the temperature. Right, this last piece of our equation, E to the negative EA over RT, is known as our exponential factor. It's a way to account for temperature effects and our reaction rates. All right, going through this in a little bit more detail here. Our first part, this frequency factor, tells us how many times will our molecules collide per unit time in that correct orientation. A large frequency factor means that we'll have many good collisions every second or hour or minute. A smaller frequency factor will tell us that there are fewer good collisions every second. If we're looking at this visually, we can think about the symmetry and orientations of our molecules visually. On the left, we have two spherical atoms, which need to collide together. There's no wrong way for two spheres to collide if they're perfectly symmetrical. However, if we have this picture on the right, we have two maybe diatomic molecules that need to collide perhaps exactly side to side. There's less symmetry for these molecules than there are for our perfect spheres. If they need to collide side to side like this, our frequency factor has to be smaller. Right? There's fewer ways to have that good collision. We're going to have fewer good collisions every second. We can examine this practice problem for a moment. Feel free to pause and see if you can get it. We're looking for the smallest frequency factor. That is going to be the molecules which have, well, the least amount of symmetry, the molecules where it's the hardest for them to collide together nicely. Hydrogen atoms and iodide atoms, these are going to be perfectly spherical things. This will have a very large frequency factor. It's easy for these to collide together. Our diatomic molecules here, well, as we saw on the previous slide, this will be harder to do correctly. We're going to have a smaller frequency factor. Lastly, if we have hydrogen chloride gas colliding together here, maybe this is going to be the hardest to do. We can think about these two molecules trying to collide. Maybe we have to have them exactly side to side so that our hydrogens can line up and our chlorides can line up, trying to form these two products. This seems like the hardest thing to do because we have the least symmetrical molecules. All right, our second part of our Arrhenius equation, that exponential part, relates our reaction coordinate and our temperature to our reaction rates. Recall our reaction coordinate. We have our starting materials trying to climb over some energy barrier to get to our products. The height of that energy barrier is known as the activation energy. When we have our starting molecules here, they need to collide together. When they do, if they have sufficient energy, they'll form that transition state. This transition state will not last. It will only be there for just a millisecond, and then it will form our products. Well, if we're thinking about what molecules, what collisions can occur with sufficient energy to overcome that barrier, we can start to think about this in terms of our Boltzmann distribution. Recall that any sample of molecules will have a variety of energies to them. There'll be a distribution of energies to our sample of molecules. Right? Not every single molecule has exactly the same energy. Some are going very slowly, some are going much more quickly, and maybe there's some average amount of energy for our sample. This curve up high in red is maybe at some colder temperature, some lower temperature sample of molecules. When we increase the temperature to T2, we shift that distribution to the right and we cause it to be more spread out. Ultimately, we have more energy in our molecules and more of our molecules will climb over that transition state and be able to reach our products. Right? On our reaction coordinate, scrolling back here, this activation energy on our reaction coordinate will correspond to some place on the x-axis of our Boltzmann distribution, right? Some amount of energy that we need to do this reaction. When we have this colder sample of gas, these molecules are able to do our reaction. When we have our hotter sample of gas, these molecules are able to do our reaction. Right? Increasing the energy allows more of these reactions to occur. Notice here, we're shading, well, the area under the curve on this Boltzmann distribution to show, well, how many of these molecules, what fraction of these molecules have sufficient energy to do our reaction. Well, this is related exactly to that term in our Arrhenius equation. The exponential factor is exactly the area under the curve above or past that activation energy. Right? So this frequency factor represents how many of our particles have enough energy to overcome that activation energy. What is the area under the curve? What percentage or fraction of our molecules are able to do this reaction? As our temperature gets bigger, this value also gets bigger. As our activation energy changes, right? As we shift this activation energy left or right, we can have more or less molecules able to do that reaction. Right? Once again, if there's a shorter hill to climb over, more of our molecules are able to do it. Right? Imagine if we have maybe a different mechanism and we change our activation energy to be this value. Well, all of a sudden we have maybe a lot more molecules that are able to do it. Numerically, we can use our expression here to figure out exactly what that percentage is. Okay, we can tie this all together, right? Our Arrhenius equation, once again, it's relating our rate constant to some numerical values, right? We can use our collision theory ideas to numerically determine our rate constant, or vice versa. Our reactions go fast when we have a large rate constant. Our reactions go slowly when we have a smaller rate constant. What allows our rate constant to be big? Well, when we have a big frequency factor, when we have lots of good collisions occurring. Alternatively, we could have a low activation energy. Or alternatively, we could just have a very high temperature. We could just have a lot of these molecules going very quickly and overcoming that energy barrier. We can look at a practice problem. Here we have measured the rate constant, we've measured the frequency factor, and we know what the temperature is. Well, if we know all these things, we can determine the last unknown. We can try to solve for this activation energy. Please take a moment, see if you can try to find the answer. If you got a value of 84 kilojoules per mole, I believe that is correct. All right, now we've seen our Arrhenius equation in this first form. We can have a few other options as well. If we take the natural log of this equation, we can get a different form. Well, same equation, different form, but now it's more linear when we graph the natural log of the rate constant versus 1 over the temperature. Right? We can get this in the form of y equals mx plus b, where our y value is natural log of the rate constant, and our x value is inverse temperature. Interesting. Or if we want to make this equation just a 2-point equation, right? Compare the rate constant at exactly 2 different temperatures, then we can remove our frequency factor from the equation entirely, and we get this third form of the equation. We'd like to be able to utilize all 3 of these approaches, depending on what is maybe most convenient. And so, okay, let's look at one last practice problem here. We've measured the rate constant at 2 different temperatures. Can we use this to find the activation energy? Well, it seems like this is a good form of our equation. We've measured 2 rate constants at 2 different temperatures. R is just the gas constant. We can figure out EA. One last practice problem if you're feeling ambitious. And there we go. This is our discussion on the Arrhenius equation, trying to go back to collision theory, introduce a little bit of math, and now we can solve some more numerical problems with our intuition about collision theory. Thank you so much. Please let me know if you have any questions. I hope to see you in the next video, and I hope you have a great rest of your day.